Title of the module, Introduction to Graphs. We welcome you to the massive open online course Graph Theory. In this first session, we are going to deal with the introduction to graphs. Graph theory is an important area of contemporary mathematics with many applications in computer science, genetics, chemistry, engineering, industry, business, and social sciences. It is a young science invented and developing for solving challenging problems of computerized society for which traditional area of mathematics such as algebra or calculus are powerless. Many real-world situations can conveniently be described by means of a diagram consisting of a set of points together with lines joining certain pairs of these points. For example, the points could represent people with lines joining pairs of friends, or the points might be communication centers with lines representing communication links. Notice that in such pictures, one is mainly interested in whether or not two given points are joined by a line. The manner in which they are joined is immaterial. A mathematical abstraction of situations of this type give rise to the concept of a graph. The 7 bridges of Königsberg is a historically notable problem in mathematics. Its negative resolution by Leonhard Euler in 1736 laid the foundations of graph theory. The city of Königsberg in Prussia was set on both sides of the Pregel River and included 2 large islands, Neiphof and Lomsee, which were connected to each other or to the 2 mainland portions of the city by 7 bridges. The problem was to devise a walk through the city that would cross each of those bridges once and only once. By way of specifying the logical task unambiguously, solutions involving either number 1, reaching an island or mainland bank other than via one of the bridges, or number 2, accessing any bridge without crossing to its other end, are explicitly unacceptable. Euler proved that the problem has no solution. The difficulty he faced was the development of a suitable technique of analysis and of subsequent tests that established this assertion with mathematical rigor. The graph is a set of points in a plane or in a space and a set of a line segment of the curve, each of which either joins 2 points or they join to itself. Let us now see the definition of a graph. A graph G is equal to V of G, E of G consisting of 2 finite steps. V of G, the vertex set of the graph, is denoted by V, which is a non-empty set of elements called vertices, and E of G, the edge set of the graph, often denoted by just E, which is a possibly empty set of elements called edges. Each edge E in capital E has a set of 1 or 2 vertices associated to it, which are called its endpoints. A vertex may exist in a graph and not belong to an edge. V and E are usually taken to be finite, and many of the well-known results are not true for infinite graphs because many of the arguments fail in the infinite case. The order of a graph is denoted by cardinality of V, its number of vertices. The size of a graph is cardinality of E, its number of edges. If 2 vertices are connected by an edge, then they are called adjacent, otherwise they are called disjoint. The maximum degree of a graph G, delta of G, is equal to the maximum of all degrees of V such that V belongs to V of G. Similarly, the minimum degree of a graph G, delta of G, is equal to minimum of degree of V such that V belongs to capital V of G. We shall now see some of the preliminary definitions of graph theory with the help of examples. See, on this board, I have first drawn a simple graph A simple graph is nothing but it contains some vertices. So, A, B, C and D. So, these are the points here. So, you can see that I have put a black dot. So, these are points or vertices, and the lines connecting the two vertices are said to be edges. So, G of V comma E is the vertex set consists of A, B, C, D, and the edge set consists of, so AB is an edge, AC is an edge, AD is an edge and BC is an edge. So, I have drawn all these edges and they have been represented in the edge set. You can even name them as E1, E2, E3, E4 etc. So, depending on how many number of edges you have, you can name them as V1, V2, E1, E2 etc. So, vertices also likewise, and this is how you represent a simple graph. Now, let us see what a multigraph is. A multigraph is one in which there is existing more than one edge between any two vertices. So, in the previous simple graph you can see there is only one edge between these two vertices and there is no loop. So, this is called a loop. It is looping in back to itself. So, from B there is an edge E4 starting at B and ending at B itself. This is called a loop, and this is called a parallel edge because between B and C there is one edge here E6 and there is one more edge E5 as well. So, these are said to be parallel edges, so or two different paths from the same two vertices, namely B and C. So, this is a prime example of a multigraph. A multigraph will contain parallel edges as well as loops, or even just one. Even if it has just a loop, it is said to be a multigraph, or even if it has only parallel edges, it is also said to be a multigraph. They can either have one or both the characteristics. So, this is a multigraph and this is a simple graph. So, you can clearly make the distinction between these two types of graphs. Now, let us move on to one more concept, which is the connected graph. A graph can either be connected or disconnected. In a connected graph, there exists a path between every two vertices. So, that is the basic tenet of a connected graph. There exists a path between any two vertices. So, here this is an example of a connected graph. You can see that, let us say randomly, let me choose, let us say I need a path between E and J. So, from E, is there a path from E to J? Yes, because I can go from E to F, F to G and then G to J. Obviously, there is a path between E and J. So, you can randomly choose any two vertices, and between every two pair of vertices you will be able to find a path. That is the example of a connected graph. And then a disconnected graph is one in which if you can find even one pair of vertices between which there are no paths, then it is said to be a disconnected graph. Now, let us look at this graph. For example, here between B and D there is a path, B, C, D. So, B and D there is a path, but there is no path between B and E. So, between B and E, can you find a path? So, this is C, this is E. So, can you find a path between B and E? No, obviously it is no, because there is no path between B and E, and therefore, this graph is said to be a disconnected graph. And they can also be classified as components. For example, here in this graph we have two components. So, this is one component, A, B, C, D is one component and E, F, G, H is another component. So, you can have multiple components in a disconnected graph, but in a connected graph there is only one component. You cannot have two or three components in a connected graph. So, that is the biggest difference between a connected and a disconnected graph. Now, let us come to the degree of a graph. Let us take for example this connected graph itself. The maximum degree is denoted by delta of G. So, this is this delta, capital delta of G, and this is del. So, del of G is also called as small delta. So, this is del and this is delta. Let us make that distinction here itself, and you can have a look at this graph and find out which vertex is having the maximum degree. So, here you can see B has got degree 2 because there are two edges here, one AB is one edge, BC is one edge. About E, but when you look at E, you have CE is one edge, EF is one edge and EH is one edge. So, the degree of E is 3. So, this is how you calculate the degree of a graph. The degree of the graph is the number of edges impinging on it. So, every vertex, if you are calculating, A has got 3 edges impinging on it, D has got 2 edges impinging on it, C has got 3 edges, E has got 3 edges, F has got 2 edges, G has got 3 edges and H has got 2 edges. So, clearly the maximum degree is 3, because there are several vertices that have maximum degree 3. Suppose you are able to find a vertex which has got the maximum degree as 4, then automatically delta of G will become 4, but with regard to this graph, delta of G is equal to 3. Now, what is the minimum degree? It is the least degree. What is the delta of G is, it's a minimum degree. Del of G is equal to 2, because B has got degree 2, F has got degree 2, there is no vertex of degree 1. If there were, then that will become automatically the minimum degree, but with regard to this graph, you have the minimum degree as 2, and therefore delta of G is equal to 3 and del of G is equal to 2. So, using this we have now studied maximum degree, the minimum degree, and we have seen a connected graph and a disconnected graph. Now, let us move on to something called the complete graph. The complete graph is one of the most important graphs in in graph theory, and here you can see that this is a complete graph on 3 vertices. So, A, B and C, 3 vertices, all the 3 vertices are connected by edges. A complete graph is one in which every vertex is connected to every other vertex by means of an edge. And in G2, can you see there are 4 vertices? You can see that A is connected to B, A is connected to C and A is connected to D as well. So, every vertex is connected to every other vertex, and likewise for B, B is connected to A, B is connected to C and B is connected to D. So, this is how you construct a complete graph. Given any number of vertices, if I give you 5 vertices, you might arrive at a pentagonal structure with all the vertices connecting each other and all. So, we can keep on constructing bigger number of vertices. So, this is a basic example. A complete graph is one in which every vertex is connected to every other vertex. That is the definition. Now, let us move on to something called the bipartite graph. Now, a bipartite graph is one in which the set of vertices has been split into 2. That is the meaning of bi. So, bi means 2. So, 2 different sets, the vertex set V has been differentiated into U and V. So, U and V are 2 different subsets of the vertex set. So, here inside U there are U1 and U2, and in V there are V1, V2 and V3. So, 3 vertices here and 2 vertices here, and they are connected. Whatever edges are there between these 2 sets are represented here by U1 V1, U1 V2, U2 V3. One more important constraint in a bipartite graph is that these 2 vertices will not have edges at all. So, between U1 and U2 you do not have an edge, and between these V1, V2 and V3 also you do not have edges. So, in a bipartite graph the edges will always happen from one set to the other set. So, that is the meaning of a bipartite graph. Complete bipartite graph, you can see this example. In a complete bipartite graph, every vertex in U is connected to every other vertex in V. So, U1 is connected to V1, U1 is connected to V2, U1 is connected to V3. Likewise, U2 is connected to V1, U2 is connected to V2 and U2 is connected to V3. So, this is an example of a complete bipartite graph. So, bipartite means 2 partitions of the vertex set, and these 2 partitions are connected to each other by means of edges. Complete bipartite is where every vertex is connected to every other vertex in the other partition. So, I am sure that this part is clear. So, bipartite and complete bipartite graph is done. Next we come to something called the complement graph. I have drawn a very simple graph. This is actually something called the 4 cycle, and this the cycle, the path, the walk, these kinds of things we will be discussing in detail later on in the upcoming modules. But for now, let us see that this is a simple graph on 4 vertices, and these vertices, and it is a connected graph. Keeping in mind the definition of connectedness that we just studied, this is a connected graph. Now, A to B there is an edge, B to C there is an edge, C to D there is an edge, and D to A there is an edge. Now, you just have to reverse it or invert the graph, which means that between A and B, if there is an edge here, the complement will not have the same edge. So, the vertices are taken into the complement graph, but not the edges. So, you have A, B, C, D vertices, you have A, B, C, D vertices here in the complement graph as well, but you do not connect them by the same edges here. So, if AB is an edge in G, G complement does not have AB as an edge. If AD is an edge in G, G complement does not have AD, and BC is an edge in G, but BC is not an edge in G complement, likewise for DC. So, what are the edges then? Anything which is not an edge in G will become an edge in G complement. So, AC is not an edge in the G, but it is an edge in G complement. BD is not an edge in G, but it is an edge in G complement. So, this is the example of constructing a complement graph by giving you a graph and then constructing the complement using just the vertices, but omitting the edges, but constructing new edges whenever the original edges are not present in the earlier graph. So, next we come to something called the regular graph. The regular graph is one in which all the vertices have the same degree. Now, let us suppose you have fixed the degree of the graph to be 2. Then every vertex in that graph will have a 2 regular graph is one in which every vertex in the graph will have degree 2. A 3 regular graph is one in which every vertex of the graph has got degree 3. We already saw what is a degree. It is the number of edges impinging on that vertex. So, here we can see that it is a 3 regular graph because A, B, C, D, E, F, all of these are vertices. You can see the number of edges impinging on A is 1, 2, 3. So, 3 edges are impinging on A, the degree is 3. What about B? B also has got 3 edges. We got AB, we got HB, you got BC. So, 3 edges are impinging on this vertex and therefore, 3 edges there, and therefore, the degree of B is 3. Likewise, for C, you can clearly see that there are 3 edges coming from here to here to here, therefore, 3 edges here. H has got 3 edges, it has got GH, it has got HB, it has got HD. Therefore, 3 edges at H as well, at G also. So, very clearly it is obvious that this graph, every vertex in this graph has got degree 3, which means it is a 3 regular graph, or you can call them a regular graph. A regular graph is one in which there is a constant degree for all the vertices. Next, we come to something called the directed graph. Now, so far whatever we saw is just a simple graph, but the directed graph is one in which you have very clearly denoted arcs. An arc is an ordered pair. Suppose I say AB is the ordered pair and it is the arc, then it means that there is a path from A to B, but not from B to A. The arc is from, it is an ordered pair. We already know that the ordered pair means something comes first and the next thing comes later. So, it is ordered. So, in a directed graph, now AB you can see that this is an arc. It is no longer called an edge. It is actually an arc, but sometimes we switch the terminologies once in a while. So, AB is an arc and from A to B there is a path. From A to B there is a arc going from A to B, but not from B to A. So, there is a clear distinction, and then from E to A there is an arc, that is A comma E. So, from A comes first and it goes to E. So, A to, it is like a one way traffic. So, we all know how certain roads act as one way. Like this, in a directed graph it is a one way. So, you just can go in one direction, you cannot go in the opposite direction. But the general understanding is that in a simple graph or in an undirected graph you can go both ways. That is the understanding, but in a directed graph you can only go in the direction in which the arrow is pointing. That is why it is called an arc. So, this is an example of a directed graph. We just saw some definitions of graph theory. These are some basic definitions. I hope that you were able to understand them. Now, for example, in the regular graph, you were able to see that all the vertices of the graph are having the same degree, which means that the minimum and the maximum degree are the same. So, you can extrapolate some results from each of these graphs. And there is something called the empty graph, an empty graph in which there are n vertices but no edges. So, these are only disparate points lying scattered, but they have no edges, which means that the number of vertices is n and the size, or which is the number of edges of the graph, is equal to 0. So, this is an empty graph. Now, let us see some applications of graph. Some applications are, graphs can be used to model many types of relations and processes in typical biological, social and information systems. Many practical problems can be represented by graphs. Emphasizing their application to real-world systems, the term networks is sometimes defined to mean a graph in which attributes are associated with the vertices and edges, and the subject that expresses and understands the real world systems as a network is called network science. In electrical engineering, the concepts of graph theory is used extensively in designing circuit connections. The types or organization of connections are named as topologies. Some examples of topologies are a star, bridge, series, and parallel topologies. In computer science, graph theory is used for the study of algorithms. For example, Kruskal's algorithm, Prim's algorithm, Dijkstra's algorithm, etc. In computer network, the relationships among interconnected computers in the network follows the principles of graph theory. In science, the molecular structure and chemical structure of a substance, the DNA structure of an organism, etc. are represented by graphs. In linguistics, the parsing tree of a language and the grammar of a language uses graphs. In general, the routes between the cities can be represented using graphs. Depicting hierarchical ordered information such as a family tree can be used as a special type of graph called tree. Next, we shall see the definition of a subgraph. A subgraph S of a graph G is a graph whose set of vertices and set of edges are all subsets of G. Since every set is a subset of itself, every graph is a subgraph of itself. All the edges and vertices of G might not be present in S, but if a vertex is present in S, it has a corresponding vertex in G, and any edge that connects two vertices in S will also connect the corresponding vertices in G. All of these graphs are subgraphs of the first graph. A vertex-induced subgraph is one that consists of some of the vertices of the original graph and all of the edges that connect them in the original. An edge-induced subgraph consists of some of the edges of the original graph and the vertices that are at their endpoints. The second two figures as shown in the screen are vertex-induced subgraphs of the first figure. The second two figures are edge-induced subgraphs of the first figure. The second figure is a subgraph of the first figure, but it is neither edge-induced nor vertex-induced. Graphs come with various properties which are used for the characterization of graphs depending on their structures. These properties are defined in specific terms pertaining to the domain of graph theory. In this chapter, we will discuss a few basic properties that are common in all the graphs. Once again, let us recall the basic concepts of graph theory. A graph is a mathematical structure consisting of a set of points called vertices and a set, possibly empty, of lines linking some pair of vertices. It is possible for the edges to be oriented, that is, to be directed edges. The lines are called edges if they are undirected, and they are called arcs if they are directed. Loop and multiple edges. A loop is an edge that connects a vertex to itself if a graph has more than one edge joining some pair of vertices, then these edges are called multiple edges. A simple graph. A simple graph is a graph that does not have more than one edge between any two vertices and no edge starts and ends at the same vertex. In other words, a simple graph is a graph without loops and multiple edges. Adjacent vertices. Two vertices are said to be adjacent if there is an edge or an arc connecting them. Adjacent edges. Adjacent edges are edges that share a common vertex. The degree of a vertex. The degree of a vertex is the number of edges incident with that vertex. A connected graph. A graph is said to be connected if any two of its vertices are joined by a path. A graph that is not connected is a disconnected graph. A disconnected graph is made up of connected subgraphs that are called components. I hope that this session gives a basic knowledge of graph theory. We will meet in the upcoming sessions with more exciting facts of graphs. Stay with us till the end. The more you learn, the more you gain knowledge. So learn more about graph theory with us. Thank you.